Okay, so thank you all for joining us today and supporting this initiative. Um, Thank you for your support. So, as you know, this initiative is with GEWEX GHP panel, and it's been our second year. I think we are, conducting this kind of meeting, monthly meeting, and after that, we are going to synthesize the results and write a report to GHP. We will be sharing the report online, so you can, contribute if you have any kind of publication or anything you want to cite it. Would be happy to look at it and then consider it in the report. So I'm going to send you guys the website of the or speaker, so you can have a really sense of what's going on with this initiative. And just a quick reminder, next month we do not have any kind of monthly meeting in a month of July because we'll be at a GHP panel. So we start back up in August or monthly meeting. So thank you all. Today we have Professor Stephen Kollet talking about some kind of interesting work. I don't need to introduce him. He is well known, one of our leading kind of scientists in the area of hydrology and groundwater modeling. Let's see. You guys can, if you have any question at the end of his presentation, you can ask Stephen. So, Stephen, are you ready to share your PowerPoint?
Yeah,
Great, thank you.
thank you. Thank you very much. And thank you very much for giving us, Laura and I, the opportunity to present um, some work we are doing in the Global Groundwater Network in GHP. Oh, one second. Now I have. Okay. Now it works. Exactly, yes. So I think I do not have to really introduce where the GHP's panel sits in GEWEX. And in GEWEX, there are different types of projects, and we are basically a network at this point, which has a runtime of 1 to 2 years. And and then the idea is to basically move the network to a more like a research project. So we have a steering group that we have been setting up for 2 years ago, I think, consisting of different people, experts in hydrogeology and groundwater modeling from different regions of the world, and we are still soliciting, of course, also members in the groundwater network and trying to really have a nice diversity in geographic coverage and also with respect to young career scientists and so on, right? So today I just want to briefly introduce the idea of our global groundwater network and what has happened previously and is currently ongoing. And since this is a flat crosscut, so I was thinking also to maybe talk a little bit about the role of groundwater in, let's say, processes of flooding and also modeling. Okay, so you have seen this picture before, and I will not repeat the details here. I just want to make a couple of points that I feel are really important, also to understand why we feel that groundwater is important in the context of GEWEX. So what we have is here we have the hydrologic cycle, and the main parts are that we have advection from the oceans toward the continent. And then what we observe on the continent is that usually precipitation from this atmospheric moisture advection is generally larger than than evaporation or evapotranspiration. And that kind of principle really holds also over large regions and also over very arid regions, actually. So as I said, precipitation is generally larger than evapotranspiration. Why? Because the continent is really like a sink for atmospheric water. And so to actually keep the continent really in a dynamic equilibrium, let's say from the source areas to the sink areas, the oceans, we need a number of different processes, and groundwater really plays a major role here, and basically transferring water from the ridges, from the recharge zones towards the continental river corridors in terms of base flow. So groundwater, we argue, is really a key here in maintaining this very delicate continental water equilibrium. And of course, that equilibrium is under major change. Why? Because of regime changes and precipitation, and also evapotranspiration. And then, of course, also because of base level change along the sink areas, right? And then another major aspect is, of course, the influence of humans. So we have a number of very strong human interventions related to, for example, groundwater abstraction and irrigation. So bottom line is, well, we have a changing continental water equilibrium that is indeed feeding back with the atmosphere, and we need to consider this in our projections and predictions. So yeah, so groundwater needs to be well represented in Earth system modeling. And that means for us, really hydrogeologists and groundwater modelers need to be involved in the Earth system modeling community. Okay, so from the Earth system modeling perspective, there is a big push really to going for high resolution. And the idea here is not only if I can't do anything else, I increase resolution. The idea really is here to improve biases in ESM projections and over certain regions. And that means also that, for example, groundwater needs to be incorporated in these ESMs. Why? Because you suddenly see at high resolution, you suddenly see really the river corridors developing because of, as I said, convergence of base flow. And in the, let's say, the current ESM models, if you increase resolution, you don't see the river corridors. And that has to do, for example, that lateral groundwater flow is missing, right? And there, of course, people have recognized this, and they started implementing groundwater parameterizations in climate models and weather and climate models, and now basically ESMs at the global scale. And even those approximations or parameterizations are really based on already like Darcy type of gradient-based implementations, right? But what you see here is really they are applied at different scales, right? And it's not really clear how you would, for example, parameterize subsurface heterogeneity because of hydrogeology, for example, right? So this is also a major part that is still missing. So what do we want to do here? We really want to constructively link NGGN. We want to constructively link hydrogeology and groundwater modeling to Earth system modeling in GHP. And we focus currently on bringing the hydrogeologic perspective to the challenges, and I will get to the challenges. So we are really encouraging hydrogeologist experts to actively participate in the network by contributing their expertise and actively shaping the groundwater modeling agenda in ESM. And that's what is also a little bit more detailed here, really building a strong community, establish a strong and consistent voice of hydrogeology and groundwater in GEWEX. And then we want to really identify ESM community projects where we can connect and dispatch hydrogeologists and groundwater modelers into WCRP to really see what's going on and get a voice. And of course, there's also a big component with respect to education and training. Ultimately, in the first 1 or 2 years, we are really working on a scientific agenda of hydrogeology and groundwater modeling in ESM and GEWEX. That's the basic idea. Okay, I have to move this. Yeah, and I think there is this very strong expertise already in large-scale hydrogeologic and groundwater flow modeling. So there are always two components to this, right? There's a flow model, right? That is basically based on the partial differential equations, the governing equations, and defining a boundary value problem and an initial value problem. On top, there's also the component of the hydrogeologic model. So how do we represent hydrologic geology, hydrogeologic heterogeneity, at scale, right? And as I said, there is a lot of experience in this, and not only for the past years, but also for the past decades, I would argue. And this is what we want to bring to the table. I point out here some examples. For example, this is the work from Laura and Reed over the United States, the Konos domain. There are other implementations of different types of numerical models, also with very sophisticated hydrogeology, for example, over China. We have from colleagues from Alan McDonald from the BGS. They develop a very nice conceptual and let's say hydrogeologic topology models of hydrogeologic heterogeneity, for example, over the African continent, that is also used to map here, for example, groundwater recharge in Africa, including also uncertainty estimates. And this is an example from the USGS where they actually realized that they need to have, for example, interactive evapotranspiration, so meaning depending on soil moisture and also on groundwater dynamics, to arrive at better estimates of groundwater recharge, which actually constitutes already, let's say a strong component of connecting to Earth system models that incorporate also land surface processes. And then there's also our work where we have been doing this for quite a while, really closing the water cycle from the bedrock across the land surface into the atmosphere. We have been working a lot at the continental scale to have interactive evapotranspiration and also precipitation, so feedbacks with the atmosphere. And now our push is really to move to the global scale. We have our first global scale 3D variably saturated groundwater flow model and surface water flow model, as I said, at the global scale, and have been doing quite some work with the Max Planck Institute in Hamburg to connect to the ICON ESM ecosystem. And to do first, let's say, latitude belt simulations, also to account for feedbacks with the atmosphere. So there are already these developments going on, but there is no formalized, let's say, involvement of really hydrogeologic and groundwater modeling experts, and that's where we want to get at. So past and future activities, we had a lot of online meetings, steering group meetings, working group meetings, all started at really the GEWEX Open Conference in Sao Paulo in 2024. We had EGU Splinter meetings and so on. There's a town hall meeting coming up at the Groundwater Modeling and More Conference in Princeton in June. And then I would really like to point out this session and workshop at the IIH, I don't know why the S is here, conference in Budapest. And during these meetings, I would argue we basically we identified many different challenges and also a way forward. I think the meeting in Ningbo we had in April was really very productive. We had a number of scientific talks also from ESM modelers. And we had a few experts from around the world on hydrogeology and groundwater modeling. And so what we can summarize from these meetings so far is that one recurring question that is coming up, of course, at what level of model complexity is really required to both general and specific scientific, and to answer really specific and general scientific and applied questions in hydrogeological representation, numerical groundwater modeling, and also observational frameworks. Of course, always given the challenge of this kind of ubiquitous uncertainty related to, for example, aquifer heterogeneity. That's the overarching question, right? So we really have to address hydrologic representation at scale. We have to address groundwater flow models. So what is the theory really at scale? And then how do you address the observational challenge, from in situ to remotely sensed? So that is really what we are working on. Okay. So currently, we developed a concept, and I will get to this a little bit in the coming slide. And we submitted a BAMS proposal and working on the manuscript. So the BAMS proposal has been submitted, and so I think or accepted, and I think we will be ready with a nice manuscript in a few months. Okay, in this manuscript, we argue for the evolution of groundwater representation and system models. Let's say for more like an interface thinking towards a continuum framework, right? So there's been a very influential white paper, I think 2005, on groundwater fluxes across interfaces. And of course, there has been this very famous Fries and Hahn blueprint of a water continuum framework with respect to the terrestrial water cycle. And that's what we want to implement actually. And we want to bring this to this water continuum framework. We want to bring the groundwater perspective. Based on these arguments we had at the beginning, that really groundwater plays the major role in the water continuum on the continent, and thus the feedback also with the atmosphere. Okay, now I come to the role of groundwater in flooding. I think personally that the role of groundwater in flooding cannot be underestimated or should not be underestimated. And so it really plays already directly into this to this water continuum thinking. So where we say, okay, in terms of subsurface water, the saturated zone and the unsaturated zone and surface water, this is indeed one continuum. And we can already treat this as a continuum in our numerical models by basically using, for example, surface water flow equations to close the mathematical problem of water redistribution in the subsurface. And that gives us a lot of, let's say, mechanistic understanding of how groundwater plays into the process of flooding at different scales. And we have been doing this for quite a while using the integrated hydrogeological model and surface water flow model PARFlow. And I want to show you sometimes also very basic examples to make the case that really groundwater is also key in many processes of flooding. So what you see here is this is like a benchmark problem we have been using in the past to benchmark numerical integrated models, hydrologic models, and also more parameterized hydrogeologic models. So it's a really just like a cross section here, what you see here. And we call it the so-called slab benchmark. Why? Because we have two distinct slabs, heterogeneities of subsurface heterogeneity in the domain. Here we have a slab on the left where the saturated hydraulic conductivity of that slab is larger than the precipitation rate we rain on this domain. And then we have a hydraulic conductivity of the slab here in the middle that is smaller than the precipitation rate. So what we do is we rain on that slab for a certain period of time, and then we have a recession period. You see here, this is really like a scale independence. So you have L prime and D prime. So the width, dimensional width of this cross section and the dimensional depth of the cross section. So you could scale this up and down as you wish. So this is really, these are simulations using 3D Richards equation at the support scale. So this is really at the resolution where the Richards equation really holds. And we observe here the key major processes of flooding. So here, of course, in the middle of the domain where we have the hydraulic conductivity being smaller than the precipitation rate, we have, for example, a Hortonian runoff, where we have kind of immediate ponding of water along that region, which is following the topographic gradient. It's also here re-infiltrating. Then we have sort of flooding here. It's kind of a spring type of flooding because of shallow subsurface heterogeneity, where we develop like a perched water table that is then exiting at the land surface and creating sort of like a seepage phase, which can also be one of the major processes of flooding. And then, of course, we have here the typical excess saturation flooding, where we really have suddenly an interception of the groundwater table with the land surface causing, for example, large-scale flooding, which has been observed in many different cases. So this is really, I would argue, a kind of a toy problem. It has all the complexity already, and it's actually it has been shown to be quite difficult for many numerical models to reproduce. But I think it's very nicely illustrating, why variably saturated subsurface flow, including groundwater, of course, is key in the different processes of flooding. You can already see here that, for example, continuity of heterogeneity and the saturated hydraulic conductivity here along the land surface will play a major role in how, for example, Houghtonnian runoff occurs. For example, here because of hydrophobic crusting, maybe because of also human-influenced landscapes, for example, in agricultural landscapes and so on. But you see here, for example, if you really honor the reinfiltration process here at the end of this little slab, you see that spatial continuity of these areas really will play a major role on how flooding manifests itself after strong rainfall events. Okay, and we have also been investigating this with stochastic simulations to understand how spatial continuity of this heterogeneity comes into play. And you see here, so basically we generated a spatially correlated random fields. This is a map of the random field, but it really goes into 3D. And we then simulated like a flood hydrograph that you show here. And what we do is we basically simulate the spatial distribution of hydraulic conductivity around a mean value. And then we look at the total fractional outflow. That means how much water flows out relative to the amount we rain on. Here, what you see is this is a non-dimensional rain rate. When you see here, which is smaller than 1, then that means really that the mean hydraulic conductivity is smaller than the rain rate. If it's 1, it's equal, and if it's larger than 1, it's the rain rate is larger than the mean hydraulic conductivity. And then we also change the variance of the field, by up to 5 orders of magnitude, right? And what you see here is this is like the average outflow rate that is expected. And you see, for example, that if your mean hydraulic conductivity is smaller than the rain rate, then you see there is no real way how you would be able to arrive at a mean hill slope, so to say, right? So really the outflow rate, the fractional outflow rate is always smaller than the mean outflow rate for a effective, let's say, hill slope. If the rainfall is larger than the hydraulic conductivity, it seems like that you arrive at something like a mean behavior of your hill slope and your subsurface, but you only do that for very large hill slopes. This is a multiple of the integral scale of your heterogeneity. So the bottom line is that you might not be able actually to arrive at a meaningful average representation of a hill slope because there's no ergodic behavior of your, let's say, flow field. So that also then, of course, directly applies to connectivity at the large scale and where it matters. And we have to acknowledge that this kind of connectivity and average behavior of a hill slope may not generally exist, right? And that really should shape our thinking about these types of maps that have been produced for quite some time, where here we have a forcing-based, multi-forcing-based, observational-based global runoff reanalysis, a GRUN, and which shows runoff with respect to subsurface flow and surface water flow. And I feel that in many places or in many cases, people view that these kinds of runoff maps are mostly dominated by surface runoff. And I believe this is actually not the case. I think in the mass majority of runoff, also in runoff from floods, actually here really subsurface water dominates the actual outflow. Another aspect I think that gets really missed is that flooding is to large degree a pressure response. So we know that we have convergence of base flow towards the river corridor. We load the watershed, the hill slopes with this, for example, continuous rain, and that causes actually a pressure response right along the river corridor, where the water converges. And I feel a very good indicator for this type of pressure response is the water age. And there are many groups that have been shown that actually catchment storm response is actually dominated by pre-event water, so meaning really older water. Uh, uh, in contrary to the general opinion that storm flow, water from storm flow is really just pre-event water from precipitation. This is an example here from a research site or research catchment in Switzerland, where they basically analyzed with isotopes a number of storm events over well, a relatively short period. But what you see is really that except in two storm events, the storm water flow in the river was very much dominated by pre-event water. So really older water, which really indicates also that there is a very strong pressure response due to the precipitation loading in the watershed along the river corridor. Okay, my conclusion is here really that if you think about groundwater and with respect to Earth system modeling, that it's really time to inject hydrogeology and groundwater modeling into global Earth system modeling and into our thinking really. How do we parameterize the subsurface at scale? Which type of equations are we going to use at scale? And specifically to the floods crosscut, I feel that the role of groundwater in flooding should not really be underestimated for the reasons I've been discussing in the last 10 minutes. So thank you very much, and I'm happy to answer questions.
Great, great presentation. Hello, what's going on? Yes, great presentation, Stephen. Thank you very much. Wonderful. Is there any question for Stephen?
So I have a question, Stefan.
Yes.
So I think this is great. I think you make a great argument for why we need to include groundwater in flooding. I think it's a super important process, and you've really highlighted that importance. And here in Kansas, where I'm at, I see this all the time when we have floods, and it's mostly groundwater driven. I mean, it's all pressure from the precipitation, but there's so much of it that is just groundwater. Anyhow, but I guess my question is I'm really interested if you have any thoughts relative to sort of kind of studies or chunks where we could kind of work with you guys as a group to try to like get at some of these aspects of quantifying this, either from an observational point of view, doing studies, or modeling. So I don't know if you have any thoughts on how we could like actually move this forward, because I think it's super important.
Yeah, thank you. Thank you very much. Yeah, I think also Kansas, that's a good point. Yes, I think Kansas is also a very good example of groundwater flooding, actually. You rarely see in this region. I've been working in Nebraska for a long time for my PhD, and you rarely see really the type of Photonian runoff type of behavior in these regions. But so I mean, for us in GGN, so let's say the flooding has not been a priority, of course, right now. We really try to understand really how to make recommendations for ESM to implement groundwater at scale, also with respect to hydrogeologic heterogeneity. But since in these models we are thinking of using to demonstrate the feasibility of groundwater in Earth system modeling, as I said, you have implicitly all these mechanisms are in there. So in that sense, I think it would be very nice to sit down with you and design maybe some experiments, because the experiments, I think, designing experimental protocols to demonstrate that also the importance of groundwater in ESM. That could include something like also flood exercises. Yes. So in that sense, I think it would be very interesting to sit down with you and discuss maybe some useful experimental setups. Yes, in terms of numerics in connection with observations. Yes.
Yeah, I think that would be great. I'll keep thinking about that, and maybe I'll hit you up later for to ways that we can try to move that forward, because I think that would be awesome.
Thank you.
Any other question?
Yeah, I have a question. Hi, Stefan.
There's
My question is with respect to building these large-scale groundwater models. What do you think are the main problems to overcome, and how do we overcome them? I mean, we have, of course, all these large-scale geologic information, but often that's quite questionable how good that is, and uh, is that enough to build these models? There are efforts to, collect all these kind of groundwater conceptualizations from around the world as a basis to use a bit more expert knowledge that people have already more regionally pulled together. Sort of how do you see how we actually get to robust large scale models, given the unavoidable limitations of data that we have in large parts of the world?
Yeah, I think that's the that is the question that always comes up. I think what we have to remember is if you look back into history, groundwater flow modeling has been around since the advent of numerical techniques and digital computers. And actually, when you go back to literature, also also reports, we find that actually groundwater flow models also at the very large scale have been applied successfully for not only a few years, but for decades actually. And this is certainly true for groundwater flow models dealing with bulk water flow. I'm not referring to transport here, right? And the reason for that is that you can actually find um, uh, we know actually for these systems when we deal with bulk water flow, we have actually quite useful operational methods to upscale hydraulic conductivity heterogeneity. This is something that Graham Fogg has been also um, advertising for quite some time. And that is also the reason why I think these large-scale groundwater flow models have been so successful also in the past, and not the recent past, but also the previous past. I think that the challenge that we have now is to connect, let's say, more classical groundwater flow type of thinking with the Vado zone, or the very presaturated zone, and then also the land surface processes. I think that's really the challenge, and doing that at scale is not so simple. In terms of, again, also with respect to heterogeneity, right? In terms of numerics, compute, I think we have been quite successful in the past 10 years to solve the computational problem and the computational challenge. It's just a question that we have to, well, we have to apply it much broader in the community as well.
But do you think, if I can follow up with a very quick
Sure.
question, but I mean, if you compare in the papers that I've seen, which compare the current global groundwater models and their simulations, there are still quite significant differences between them. I mean, it's not that they all converge very, very closely. So they are in particular away from let's say observation-rich areas. There are quite significant differences in what they estimate. No, at least the ones I've seen.
Yeah, but
there is still some uncertainty to overcome. I mean, no.
This is provocative what I say, but I would not, I mean, you talk about the global groundwater models or global water models that, also like Robert has been comparing, right, in this recent paper.
Yeah,
right?
Robert's model and Ingrid Graf's model was in there, and models.
Yeah, but I think this is what I would not, I would not consider this groundwater representations that would a hydrogeologist or a groundwater modeler would implement. I think, for example, a major problem you have in basins that also were a focus of the paper by Inge Graf. You actually have very strong vertical flow components, which have not been, in my opinion, adequately represented. So I think it's really a question what you would well, what you consider a groundwater flow model. And I think that's where I argue that we have to bring in the hydrogeologists and also the groundwater modelers that have been doing this, for quite some time. Yeah.
Okay.
Yeah.
Great. Any other question? So, Stephen, I have a quick question, maybe a comment. You mentioned you saw several. You show several figure for hydraulic gradients. So have you guys looked into kind of changes in hydraulic gradient with respect to kind of different landscape, for example, coastal, inland? I know the coastal, we have like the hydraulic gradients, is going to be, is very gentle, right? So that we have backing up kind of groundwater inland. So have you guys looked into changes in hydraulic gradients across the globe?
So, I mean, we have done this at the continental scale. We have not been able to do this yet with our more rigorous models at the global scale. These are just what I showed you from the global modeling perspective. This is really, I would argue, these are prototype of simulations at this point. But yes, at the continental scale, we have been doing this. I think I wouldn't claim that we can do this along the coastal areas in a meaningful way because our, let's say, ocean boundary conditions are very rudimentary at best. Yeah. But I think in the interior, and interior watersheds, definitely we have been looking at this, and we can basically diagnose also at the climate time scale. We can diagnose changes in gradients and P-minus ET regimes, or basically gradients, changes in gradients because of changes in P-minus ET regimes. Yes, we can diagnose that, and we are doing this. Yes.
Great. Thank you. Thank you, Stefan. Great. Okay. So I think there's no more questions for Stephen. Let me check the chat box. I think we are good. Thank you, Stephen, for your presentation, and thank you, Laura, for supporting Stephen and attending, both of you from GHB Groundwater Network folks. Thank you very much. Okay, just a quick reminder to
I just want to say thank you again for having us.
yes.
And it's definitely worthwhile to stay in touch. Josh, I think, yes, we should definitely think about how we could basically connect. Yeah, appreciate it.
Yeah, thank you, Stephen.
Thank you. Bye.
Thank you. So I am going to again put the Google Doc every month. We send this link. So again, those of you who are new to our monthly meeting, if you have any publication related to flooding, please add your publication here so that we can consider it while we drafting the final report for GHB. And with that, Josh, do you have anything to add?
Nope, I don't think so. Thanks everyone for attending.
Yeah, just a quick reminder that we don't have our monthly meeting next month since we'll be at GHB panel. So we see you all in August, and I hope you guys continue supporting our monthly meeting. Thank you very much and have a great weekend. Thank you. Thank you, Tristan. Thank you. Bye.